Hello and welcome to the first physics videos of the first topic, measurements and uncertainties, and the first subtopic, just plain old measurements. Are you excited? No? Good. I would be scared if you were excited for measurements. This is pretty much the most basic thing that we do in physics. We measure things. And, I'm sure a lot of people watching this feel like there should be no review, but I feel like there should be review for measurements, because it's basically the base upon which we build the entire course. If your foundation is not set, your entire building will collapse in a horrible fire, and your IB career will die. We don't want that. So, we're going to start off with just making observations in physics. Making observations is how we do physics. It's what humans have been doing since the beginning of time. It's how Copernicus discovered that the sun was in the center of the solar system and not the earth, and how Einstein noticed that if you're traveling really fast and if you're standing still on the earth, light will travel in the same way because it's still 9.81 meters per second. And so, just making observations, it's how we do things. Everything you do in physics will involve an observation of some form. And those observations, we quantify them in measurements. And we quantify them in a certain way. The way that we like to call scientific notation, or as IB likes to call it, standard form, because they want you to use it all the time. Never not use it. Just use it. And basically what we do with standard form is we take our big numbers and we turn them into little numbers. Let's say you have 6,200. I mean, I know that's not a very big number, but they're probably going to want you to write in standard notation anyway. And the way that you do that is you write 6.20 times 10 to the third. Now you may be asking, how did you get there? And the answer is, well, you count the number of decimal places that you move that little decimal to make the number you originally have. You had 6.20, you've got to move it 3 over to the right to get 6,200. And that's your little integer. That's how we write all our numbers in physics, because we work with a lot of big numbers and a lot of very small numbers. If it's very small, you switch that integer to a negative, and it reverses it. It's pretty simple. So, that covered. Now we need to discuss the quantities that we use in physics, the key quantities that we will always use. The first among them, distance. Distance is pretty simple. It's the distance between two things. What do we measure it in? Meters. Meters. The little m, meters. You should have heard of them. And with that, I feel like it's a good time to try to discuss the metric system. The system that everybody in the world uses except for the backwards people in the United States of America. And I live in the United States of America, so I'm not trying to rip off anyone here, except myself. So, prefixes for the metric system. We've got your base unit, like the meter, or perhaps the liter, or the gram, and then you can go up by advances of 10. For instance, 10 times greater than 1 meter is 1 decameter. 10 times greater than that, hectometer. 10 times greater than that, kilometer, and so on and so on and so on. If you want the full list, it's in the text, actually. Let's keep going. Megameters, capital one, not a lowercase m. Gigameters, terameters, they just keep on going up. In the same way, you can go down. Centimeters, millimeters, micrometers, nanometers, picometers, femtometers, and if we get to the smallest of the small, we'll use attometers, but you probably won't see those, ever. That's really, really small. Moving on from distance. I spent too much time here. Time. Time is this weird thing that applies to basically everything in physics. So we've got to measure it. Now what do we measure it in? We measure it in seconds. If you see minutes, hours, days, years, convert them to seconds. You want them in seconds. Just like you want distance in meters, you want time in seconds. After that we move on to mass, which we measure in kilograms. And the massiveness of an object is just how much of it is there. It's not the weight. Don't confuse it with the weight. The weight is the force that gravity enacts on that object. A baseball, let's say, will have a weight on Earth, but if you put it in space, it's weightless now, right? But it still has the same mass. Always has the same mass. We measure it in kilograms. Moving on, we have volume. Volume's, it's pretty simple. It's how much space the object takes up. We measure that in meters cubed, because IB is weird. They don't want you to use liters. They want you to use meters cubed, because IB. I'll be saying that a lot in this course. Because IB. Because IB is very weird, as you've probably come to know. Then we've got density, which is kilograms meters to the negative third. Because IB also hates fractions. IB despises fractions. Fractions, IB just wants to annihilate them. It wants to abolish them. And so instead they use those funky negative exponents. So kilograms, meters to the negative 3. Yes. Which in fractions would be kilograms over meters, but why would we do that? Then displacement. This is your first introduction. I'll be covering it more in a later video of vectors, because by all means, if you initially observe it, displacement is the same thing as distance. It's the distance between 2 points. However, displacement is the shortest distance between 2 points. Let's say a circular track. Let's say you travel all the way around a circular track. Your distance is going to be the distance of the circular track, right? Your displacement should be the same. No, it's not. It's 0, because you started and ended in the same place. What's the shortest distance between the same place? There is no shortest distance because you're in the same place. So your displacement is 0. It's measured in the same units, meters, but it's a vector quantity, not a scalar one, meaning it has direction. I'll cover that more in a later video. It's going to be the 3rd video in this series if you want to skip ahead. And that covered, we have our final fundamental quantity, angle, which is angles. You should know what angles are. Degrees, radians. I don't think I have to cover that. And then we go on to SI units. We've got our base units that I've mentioned before. The base quantities are the units that you can always use that are not derived, that you can break any other unit in the universe down into some variation of these units. Meters, kilograms, seconds, we've already covered those. Distance, mass, and time. And we've got amperes, which is the basic unit for electric current, once we get into electric currents and such. We've got Kelvin, which is basic temperature. And so moles, which is used to measure the amount of atoms in a substance. You might recall Avogadro's number from back in chemistry, 6.02 times 10 to the 23rd, I believe. And then we've got candelas. Oh yeah, that's a word. It's for luminous intensity when measuring light. You know, the intensity of the light of a lamp. The intensity of the spotlights that I've got shining on me right now so there are no shadows on my face. And so those are all the basic units. You can break down any unit into those basic units. What are the other units, you may ask? Well, they are the derived units. We combine these basic units just so it's easier so we don't have to put meters times kilograms over seconds times amperes for a unit, and we can just say something else. Just make up a name. For instance, volume. That's a derived unit. That's meters cubed, right? So it's meters times meters times meters. That's not basic, it's derived. Or newtons, right? That's meters per second times kilograms. Kilograms times meters per second. It is derived. It's all those, but we gave it a name. So just be aware of that. Be aware that lots of the measurements you'll be using are derived from those basic ones. And know what those basic ones are. And so that's our first video. That's the basic concept of measuring. Next time, we'll be going into uncertainties and errors. See ya.